Hello, my name is Akshay Aravamudan, and I will be presenting our work titled Deep Residual Downscaling of Remote Sensing Imagery for Flood Hazard Assessment. This is joint work with Zimeena Rasheed, Zhang, Dr. Georgios Anagnostopoulos, Dr. Witold Krajewski, and Dr. Efthymios Nikolopoulos. We here present the results of a pilot study aimed at downscaling or upsampling low-resolution flood inundation maps to an appropriate spatial resolution. Given the tendency of human population to reside close to sources of water, it is of utmost importance to appropriately account for risks. Every year, at a global scale, flooding results in billions of dollars in damages and significant loss of lives. In the current Anthropocene epoch, climate change, in addition to population growth, has only increased this risk at a global scale. Our efforts here are motivated by a need to improve our understanding of spatiotemporal dynamics of flood hazards. To this end, flood inundation estimates at higher spatial resolution can prove quite effective in stemming said hazards. On the right, you will find a satellite image of the Missouri River flooding. This is a region of interest in our study, wherein a failure to adequately account for such dynamics resulted in damages. Flood inundation maps provide much needed information that can help in estimating risk of and potentially improving the design of critical infrastructure. It can also help in evaluating insurance risk and in post-flood mitigation strategies such as emergency response procedures. Existing remote sensing solutions are limited to either produce coarse resolution maps that have 250 to 300 meter resolution or tend to have long revisit times. This stunts any ability for proactive response. Although there are existing model-based FIMs, these are obtained through computationally intensive processes, rendering it feasible only for limited applications. In this work, we explore the viability of downscaling low-resolution flood inundation maps via a deep super-resolution technique. We investigate the utility of deep learning architectures to downscale by a factor of 10. Subsequently, we also evaluate the use of out-of-the-box solutions for downscaling. Finally, we investigate the viability of topographic information in enhancing downscaling fidelity. Our data was obtained via hydraulic simulations for the entire state of Iowa. This was obtained from the Iowa Flood Center. Our high-resolution flood inundation maps are roughly 30 meters with binary responses for each pixel, indicating a flood or no flood. We selected these FIMs developed for a return period of 25 years. From these flood inundation maps, we prepared our coarse resolution dataset by a simple aggregation with resulting pixel values expressed as a water fraction, or the percentage of pixels inundated. Another strong motivator is to allow generalizability across different regions. As a result, we could not pick finer resolutions for ground truth. Additionally, a topographic database was prepared for each flood inundation map using a 30-meter resolution. Digital elevation models were downloaded from USGS. These DEMs were used to devise two types of data. One, the vertical distance to the nearest drainage, and the horizontal distance to the nearest drainage. On the right, you will find an example of these two features for a high-resolution flood inundation map. We now describe our approach to the super-resolution task. We chose to use a residual dense network-based approach. Our primary motivation was its performance on benchmark datasets, as well as the availability and seamless modification of their code. In this work, we explore two different instances of these RDN-based models, with and without topographic features. The diagram shows a slightly high-level description of our model. It consists of a shallow feature extraction part in the beginning. This transforms the input into features that will be used by the RDBs or residual dense blocks, indicated here by the light red boxes. The RDNs use a combination of local and global residual learnings via these RDBs. The outputs from these blocks are then propagated to an upsampling block that brings the image to the dimensionality of the output. It is after this step that we concatenate topographic features, which then passes through the reconstruction stage to produce the high-resolution flood inundation maps. We use average cross entropy as our loss function. This is different from conventional super-resolution tasks that usually use mean squared error or an L1 loss. This is because our output is a pixel-wise classification of either flood or no flood. Additionally, we also use a penalty term that makes use of a soft version of the water fraction constraint. This constraint works on the principle that the proportion of flooded high-resolution pixels should be close to the water fraction of the corresponding low-resolution pixel. This soft constraint uses a hyperparameter eta, and this constraint is effectively turned off if eta is 0. Moving on to our baselines for comparison. First, we use bicubic interpolation. This method is interpolated over a 4x4 neighborhood and tends to produce smoother images with few interpolation artifacts. Next, we also use Langsauce downscaling that interpolates on an 8x8 neighborhood. This method smoothly interpolates the value of a pixel using the Langsauce kernel. We also use LAP-SRN as a baseline. This is a deep learning model used to super resolve images by making use of a Laplacian pyramid framework. The network progressively reconstructs the subband residuals of high-resolution images at multiple pyramid levels. We use a pre-trained model that was provided by the authors of the work. All of the above models were implemented using the OpenCV library on Python. The final baseline we used was developed using the topographic features. In this case, for each pixel in the low-resolution image, where the water fraction is greater than 0, we evaluated the output patch in the associated high-resolution flood inundation map. The output patch was filled with pixels until the fraction was achieved. These pixels were filled using a ranking that was determined by the values of the horizontal and vertical distances for the associated pixel. Moving on to our results. It is to be noted that due to an overwhelming presence of no flood labels in the ground truth, we needed to use a more robust measure in comparing the models. We chose Matthew's correlation coefficient. This measures the classification improvement over naive predictions, that is, one where we choose the majority class label. MCC is computed from the classification problem's 2x2 contingency table. A value of 0 signifies no improvement, whereas a value of 1 corresponds to 100% classification accuracy. The RDN-based models outperformed our baselines with respect to this metric. This slide shows a few examples to illustrate the differences between the models. We note that the RDN-based models maintain continuity in river flow in comparison to the other baseline models. While the baseline flood inundation map model tends to retain the shape from the high-resolution ground truth, they are plagued by discontinuities. So, to conclude, our results from the pilot study indicate the following. First, RDNs demonstrate superior performance to alternatives for a downscaling factor of 10. Second, we find that architectures customized to flood inundation map downscaling outperforms a few indicative computer vision baselines. And finally, our results indicate promise in improving downscaling performance using topographic features. All of these open up avenues for improvement in future work. In terms of the architecture, we can explore attention-based models and use it to evaluate how exactly topographic features may help to improve reconstruction. We can also mask the output from these deep networks with information derived from topographic features. Finally, we also intend to evaluate the performance of these models using real-world flood inundation maps. These are our references. We thank you for listening to our presentation and invite any further questions.